Okay, so for this video, we will deal with hex numbers, and then we will deal with the conversion to and from hex numbers. That is, we will take a hex number, convert it to decimal, decimal to hex, binary to hex, hex to binary. Okay, and then we will see what is really the use of, or the importance of representing numbers in hex. Okay. So again, let me just write down the objective. So we're going to be dealing with hex numbers, which is the base is 16. Okay. All right. So it has its own weights based on the fact that it has a base of 16. All right. So just like we did with just a review, when we had a base 10 value, right? So let's say we had a base 10 value, which is a decimal, right? Which is a decimal number. And let's say we had a number like this, 12, okay? Well, that 12 really meant that this one was at base 10, position 0, and this one was at base 10, position 1 in terms of weights. And then what you do is you multiply the weight by the content of the digit and add them up. So let's do that. So 1 times 10 to the 1 plus 2 times 10 to the 0. Well, that is 1 times 10 plus 2 times 1, which is really 10 plus 2, which takes us back to 12 in decimal. So you could see here we went full circle, went from 12 decimal to 12 decimal. Now what if we had binary? So we had binary here. Binary, be it the base is 2, right? So that's the base, okay? And so what do? So let's say we had this value, 1, 0, 1 in binary. Now remember, any of these digits can only go from 0 to 1, right? In decimal, any of these digits can go from 0 to 9. Okay, so the count, since decimal is base 10, you're going to count 10 times starting at 0 to 9. Here, any of these digits can go either 0 or 1. Again, so the count is 2 in terms of possible values. That is why it's base 2. But then again, we take the base and put the weight on it. The base, weight, base, weight, right? So again, this will be the weight for this one, the weight for this one, the weight for this one. And then the same process. Okay? So that would be 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0. Right? So if we break each one out, so that would be 1 times 2 to the 2 is 4. This would be a 0, so you're adding these. You're multiplying 0 by something. And this will be simply 2 to the 0 is 1, so this would be a 1. So this value is equal to 5 in decimal. So as you can see here, our objective here is to convert to decimal. Now, let's suppose you had a hex number which has a base of 16. And let's say this time we have 12 that is expressed as a hex number. Okay, so this has a weight, so does this one. So each digit will have a weight. So what will be the first weight right here for position 0? You take the base, just like I did here. Take the base, and position 0. And this would be 16 to the 1. Aha! So we're going to multiply the content of the field or the digit by its weight. And remember, any of these are converting whatever the number format you have to decimal. So in the end, we're going to find a decimal value equivalent to that 12. Well, let's do that. So now I have 1 times 16 to the 1 plus 2 times 16 to the 0. So 16 to the 1 is 16, so that's times 1. Now, what is 16 to the 0? It's a 1, and that's a 2. So what is this value? 18 in decimal. So in other words, 12 in hex is 18 in decimal. As you can see, so visually there is a shift here, so don't let that fool you, right? It just means that 12 in hex is not 12 in decimal. It has another equivalent value in decimal, and you have to go through the process of finding its equivalent value. Okay? So as you can see here, I did an informal conversion from hex to decimal. So this is a hex to decimal conversion. Can I do a reverse conversion, which means from decimal to hex? Yes, you can divide by 16, all right? Just like we did in binary, right? When we converted from decimal to binary. So again, can I do that? Can I go from decimal to hex using the division we did in the previous video? Absolutely. So this time you take your 18, which is in decimal, and you're going to divide it by the base right here. And you're going to ask yourself, how many 16s are in 18? Well, there is 1. 1 times 16 is 16. 18 minus 16 is 2. And remember now, this time will be your most significant digit, not a bit. Okay, it's not binary. And this will be the least significant digit. And you're going to read it this way. So what does that mean? That means 1 comes first, and then 2 is next. And you write H or 16 if you want as a small index here. And sure enough, so 18 in decimal is 12 in hex. So what we've just done here is a decimal to hex conversion. Okay? So now the key is, can we figure out how to count in hex just like we know how to count in decimal, in binary? Is there a special reason we need to know how to count in hex? And the answer is absolutely, because if you're not familiar with the hex numbering system or representation, you will be introduced to some letters that are used as soon as we find ourselves that, hey, the decimal equivalent for that particular value requires 2 decimal values or 2 decimal digits. But remember, here's the trick. In decimal, we want to use a single digit to count throughout the base. So if we say the base is 10, I want to use a single digit to count from 0 to 9. Then the next value after that is 10. So you're going to need an extra digit. Same thing with binary. So again, you're going to go to 0 all the way to 9. The next digit is 10. Same thing here. So you're going to go to 0, 1, and then the next digit is 10. So what is it going to look like for hex values? So it's going to start like this: 0, 1, 2. So 1 in hex is going to be exactly the same as 1 in decimal. Not a problem there. But we'll get to see later on what's going to happen here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And here's the problem. We need to count 16 things using 1 digit. Okay, well that is going to be an issue, because right now you're at 9, and if you were to express this in decimal, you're going to have to write 10, which means now you have 2 digits. That is not what we want to do. We want to count 15 times. Now obviously we're going to go from 0 to 16 equivalent in decimal. 0 to 15, That's your 16 counts. But we cannot write 1 0 here. So we're going to pick letters of the alphabet. A, B, C, D, E, and F. And guess what happens after that? 1 0. So as you can see, for all of these, we used a single digit to count 16 times. So if you had to figure out what is the equivalent in decimal for A, well, that would be 10. What is the equivalent for B? That would be 11. What would be the equivalent for C? That would be 12. What would be the equivalent for D? That would be 13. What would be the equivalent for E? That would be 14 in decimal. What would be the equivalent for F? That would be 15. Now, these are decimal equivalent values for these letters that are in hex. So if I write a little h here, so A in hex. Okay? Now, let's put it all together. Let's put here some sort of a table that shows us what. Let's count all the way up to 15. So what I'm going to do is put 0, 1, 2. So I'm going to count in decimal. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. I'm going to draw a line here so we could separate them. We could visually see what's going to happen here. Okay? So just bear with me a little bit. Now, I urge you to do the same thing so you get familiar with the progression or the counting, either in decimal, which I hope you know how to do, and we're going to do a counting in binary and hex. So we're going to compare them. So we're going to have the equivalent values for these decimal values in binary and in hex. Okay? So I'm going to draw a line here. And I'm going to write here, this is the decimal value. I want the hex value. And then once I'm done with the hex, I want the binary value. Okay, base 2. So this is base 10, base 16, and base 2. So that's the base. Right? So these are the bases that we're focused on. So I'm going to draw a line here. And we can see I already have it. It's right here. So I can transport or transpose whatever information I have here over here. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. And no, there is no G. After that, it's a new digit. You're done because you've counted from 0 to 15, which is 16 counts, which is based on the base, which means now if you go beyond that, you're going to need an extra digit, which you'll have to restart again from here. And then let's see what happens when you start from there. So you have 1, 1, 1, 2, etc. until you reach 1, 9. And then guess what? 1A. 1B, etc. Right? So once you reach 1F, right? So what happens? Well, you go this way. You're going to add 1 to the next digit, and you start again at 0. So that would be 2, 0, 2, 1, 2, 2, until you reach 2F, and then guess what? 3, 0. Okay, so that's the progression in counting beyond this combinations of from 0 to 15. So now what is this in binary? Now let me show you a quick way to fill this up. In binary, one hex digit will simply be expressed with 4 bits. And in the next video, I'm going to break it down for you, especially when I do the binary to hex and hex to binary conversion, right? And then we can demystify how that works. So right now, just take my word for it, the binary equivalent for any of these hex values is going to be expressed in 4 bits. But just to help you, so if you need 16 combinations, right? So 2 to the n equals 16. So what n do you need to get to 16? You could do a log if you want to backwards, right? You're going to find that n is 4. So you need 4 binary digits. All right? You need 4 binary digits to express any values from 0 to 15 or 16 combinations. Now, I'm going to show you a progression and how to fill this up real quick. Now, here's how you do it. Fill the most significant bit right now, take all 8 to 0. You will see in a minute how this comes out nicely. Right? So 1, 2, 3, 4, 5, 6, 7. Let me see here. Forgot this one right here. Right, it's a good thing I didn't make that mistake. Let me draw a line here so we can see what we're doing. So I have 8 zeros, which means now I have 8 ones. Okay. For some of you who are going to build counters in digital, this is going to be important in terms of assigning various frequencies for the signals. Okay. So again, this one now is going to go by the digit after the more significant bit. This one will be by 4. So 1, 2, 3, 4. So that means now I alternate every 4 with 1s. 0, 0, 0, 0, and then 1, 2, 3, 4. The next one, you're going to alternate 2 zeros to 1s. So 2 zeros, 2 1s, 2 zeros, 2 1s, 2 zeros, 2 1s, 2 zeros, 2 1s, and the least significant bit will alternate 0 1 0 1 0 1 until we reach the end. So 0 1 0 1 0 1 0 1 0 1 0 1 0, 1, 0, 1. Perfect. So now we have the binary equivalent to any of these decimal values or any of these hex values. That's going to come in really handy in our next video when we focus, the topic will be about hex to binary and binary to hex. Okay, so this table can come in really handy. So I'm going to redraw this table in the next video. Okay. And we're going to leverage it for our conversions between hex and binary. And you're going to find later on that it's an important topic because we use that a lot to abstract information that's in binary into something we can read quickly and in a shorthand form. So for example, let's say you're storing a value in memory, which is 10 in decimal, but really what you're storing is you're storing it in binary. But the way you're going to represent it most of the time is going to be in hex. Some programming languages like assembly is going to support representation in hex. So you need to be able to be comfortable with hex representation of values, either be it binary or decimal. So what we're seeing here in the binary column is a progression. This 0, 0, 0, 0, 0 is the beginning of the count, which is all zeros. This is a 1. This is a 2. So we had to convert any of these to decimal. We're going to find ourselves back here, right? So we're going to have the same values here equivalent to these binary values, okay? The important thing here is that we needed 4 binary digits to represent any combination from 0 to 15. Okay. So in the next video, again, we will concentrate on hex to binary and binary to hex video. And I will see you then.